Will this $500 million railgun change war forever? With regard to cannons that shoot projectiles using explosives, the US Navy has long had a definite technological edge over its competitors. However, conventional projectiles will gradually give way to directed energy weaponry as time goes on. One of these was the railgun, which the Navy developed over the course of more than 15 years and $500 million. Welcome to Military Zone, the one-stop channel where you can learn all about wars and deadly weapons. In today's video, we will see whether the $500 million railgun will change the world forever. In the late 1980s, research into railgun technology was actively conducted. A long-term project for theoretical and experimental study on railguns was announced at the Ballistic Research Laboratory, which later merged into the US Army Research Laboratory. Most of the early tests were motivated by scientific legacy of researchers from the Australian National University in 1984, when the majority of the work was done. The Strategic Defense Initiative's shift in research objectives towards the construction of a network of satellites to intercept ICBMs caused the US military to concentrate on creating miniaturized guided missiles that could launch from high-velocity plasma-armored railguns at high G-forces. However, the US Army Marine Corps and DARPA were given the go-ahead to develop anti-tank electromagnetic launching technology for mobile ground vehicles barely a year later, following the publication of a significant study by the Defense Science Council. Gunpowder has, in theory, been the preferred propellant for projectiles launched from guns for a very long time. The United States Navy has been developing the EMRG electromagnetic railgun since 2005. However, it has three main drawbacks. First, it makes the cartridge notably heavier. Second, because black powder ammunition is so destructive, it must be handled with particular care when being carried. And third, the muzzle velocity of projectiles propelled by gunpowder is only about 4,000 FPS. However, the electromagnetic railgun, which uses an electrically generated magnetic field, is the method to get around all of these drawbacks. The railgun is made up of a big electrical circuit that includes a power source, two parallel rails, and a moving armature, and it can shoot a projectile at a speed of up to an amazing 52,493 feet per second. Now, let's take a look at each of these. The power source. The rails are lengths of conductive metal, such as copper, that can range in length from 4 to 30 feet. The power source is an electric current that is frequently measured in millions of ammo. The armature, which is represented by a solid piece of conductive metal or conductive shoe, fills the space between the rails. A container that houses the actual missile. Some railguns employ a form of plasma armature in which a non-conductive projectile is covered within thin metal foil. Thus, the foil disappears as the energy passes through. It develops into plasma that conducts current. From the positive terminal to the power source, electricity travels up the positive rail via the armature, down the negative rail, and back to the power source. A magnetic field is formed around the wire as a result of the current flowing through it. A region where a magnetic force exists that is both strong and directed, similar to the parallel rails of a railgun. Each of these is surrounded by a magnetic field and a wire. Around the positive rail, the magnetic field lines move counterclockwise, whilst around the negative rail they move clockwise. The total magnetic field in this instance is orientated vertically and parallel to the charged wire in the electric field between the rails. The projectile that is pointed perpendicular to the magnetic field and the direction that the current is flowing through the armature are affected by the Lorentz force. The Lorentz force operates away from the power source and parallels the rails. Although long rails can lead to design issues, the force can be increased by prolonging them or raising the current. As a result, the majority of railguns use enormous currents in the millions of amp range to provide a powerful output force. The bullet then accelerates to the end of the rails opposite the power source under the influence of the Lorentz force and exits through the aperture. The circuit then collapses and the current abruptly stops. Technically, a railgun might be a fantastic option for both long-range and close-range shooting. General Atomics, which unveiled a ground-based railgun called the Blitzer in 2013, and Bay Systems, which provided the US Navy with a 32 MJ prototype back in 2007, stand out among those who have aggressively advocated the notion of developing the railgun in the US. So are you guys excited to know the rest of this war-changing weapon? Then watch the video all the way through and hit the subscribe button, hit the bell icon, and the like button to never miss a video. By 2010, the United States Naval Research Administration had put the latter to the test by breaking a record with a shot that had a power of 33 MJ. Unfortunately, there were some issues, as there often are with futuristic concepts, and the engineers had to deal with the primary issue that railguns pose. Railguns have become a bottleneck for conventional American battleships since they need a lot of electricity to fire projectiles at Mach 5 or higher. After all, a ship's propulsion system and the power needed for a railgun are inextricably linked. Even for the previously indicated 32 MJ arrangement, which requires a minimum of 15 MW and, even better, 30 MW of onboard power, the American CG-47 cruisers or DD-51 destroyers simply do not have enough power generation. Even worse, more sophisticated railguns with 64 megajoules or greater muzzle energy require ships to deliver 40 to 50 MW of even more power. Only ships from the new Zumwalt or DDX generations would be able to generate such power, which can be up to 78 MW, of which the ship itself needs roughly 20 MW for reliable functioning in order to fire a railgun projectile from on board. The power from such a ship's engine would be applied to the gun turret, enabling the weapon to fire up to 6 rounds per minute for however long was required before the power was returned to the ship's engine. The following are some drawbacks that are worth considering. Recoil force. Because of the projectile's immense muzzle velocity, the rails must resist a tremendous amount of recoil force. Due to the opposing current flows in each weapon's rails, a powerful pushing force is created that tries to drive the rails apart, forming an arc that causes rapid evaporation and significant damage to the rail and insulator surfaces. With a goal of reaching 1,000 rounds in the future, Admiral Matthew Clunder stated in 2014 that the railgun barrel service life had increased from a few dozen rounds to more than 400. However, the Office of Naval Research did not fully establish whether the 400 shots referred to the shots with full railgun power charges. The US Navy railgun was designed to fire 6 rounds per minute and have a 3,000 round service life. Scientists contend that technical advancement still places limits on humans, therefore it is not currently in its capacity to accomplish such lofty goals. They claim that finding the appropriate material for the rails of this novel cannon will take tens of thousands of hours of research and development in the field of material science. Another important component of the railgun is that it's essential to its usage in warfare is the projectile. It involves the creation of a trustworthy navigation system that enables the gun to fire at far-off targets and hit approaching missiles. The creation of such a package, however, has been a real pain. A naval request that stated the package should be constrained of a mass of less than 4.4 pounds, a diameter of less than 40 millimeters, and a volume of less than 200 cubic centimeters of the projectile without influencing its center of gravity revealed the difficulty of manufacturing the package. Additionally, it must endure a target acceleration of 40,000 grams at all access points and a threshold acceleration of at least 20,000 grams. Additionally, due to the exo-atmospheric flight, the package must have some radiation resistance and be able to operate in the presence of any plasma that may form in the bore or at the muzzle exit. Additionally, the entire list is predicted on a projectile production cost of less than $1,000. A 155mm howitzer's maximum projectile velocity is 1,260 miles per hour, although the US Office of Naval Research has recorded a maximum projectile velocity of Mach 6 or 4,600 miles per hour. But the US Department of Defense was obliged to divert the Navy's focus to hypersonic missiles and lasers after 15 years of development and more than $500 million in budget expenditures. The railgun project was also abandoned. This does not necessarily imply that one of the Zumwalt-class ships or even a more modern Navy ship will not have a railgun on board. However, it makes it clear that given the cordial relations between the United States and China, which is also actively developing its own railgun, the fleet has other priorities at the moment. Congress and the President could decide to change their minds at any time. And that is all for today. So what do you think? Will researchers and the military be able to advance the railgun project? Let us know in the comment section below, and if you enjoyed this video, leave a like, subscribe to the channel, and smash that notification bell for more content just like this one. Please spend some time watching our other videos on our channel, and we will see you in the next one.